In an experiment, we would like to explore the effect of 4 factors: enzyme concentration, temperature, pH, and stirring, yes or no, on the yield. And we work with 2 levels for each factor. So that gives us 2 to the power of 4. That's 16 combinations of low and high level for each factor. This means that we have to at least do 16 experiments in order to cover all possible combinations. The model that we would achieve would look something like this. So y depends on, well, each of the main effects: x1, the enzyme concentration; x2, the temperature; x3, the pH, and so on. But also the interactions of each of these factors, and the 3rd order interactions, and even a 4th order interaction. So that gives us 16 coefficients that we need to compute using the data. Again, we can only do that if we have 16 pieces of information, in other words, 16 measurements. So if we have 16 measurements, we will be able to compute these coefficients, the betas, and thus we will have the model. However, we won't have any information left to evaluate the model. In other words, to evaluate the significance of the model. So that's a problem. But there's a way to get around this, and that's what this video is about. It's about using a normal plot of the effects to evaluate which one of these effects coefficients are significant. So let's go to Excel to explore that. So here we are. We have the 4 main factors here, and I've put in the coefficients here in the contrast matrix to obtain all possible combinations. So up here we have the combination that we refer to as 1, because all the factors are at low level. In this combination here, we have only factor A at high level, so we call it A. In this one, B. And in this one, we have A and B at high level, so we call it AB, and so forth. Like that. As you can see, I've made room for all the interaction effects here. So in this one, we have the interaction of A and B, enzyme concentration and temperature; A and C, enzyme concentration and pH; AD, we have BC, we have BD, we have CD, we have ABC, ABD, ACD, and BCD, and ABCD. And to compute the coefficients of each of these, let's just use ABD as an example. I multiply the A coefficient by the C coefficient, and sorry, not the C, the B, of course, because it says ABD, so it should be B here, and D. And I'll just copy that all the way down here, like that. And I do the same thing for all these columns here, like that. So now we have a column of Y values. Notice that we only have one measurement for each combination. So there's no repetition here. There are no replicates. And all of these are our X values. So now we're ready to do regression. So I go into data analysis here, choose regression. And then I have to select my Y values, my response, my output, and the X values. And notice I include the labels here. I tick this box, which is labels, and I choose an output area, which I'll select to be this one, and hit OK. So here's the output. And notice that we have all the coefficients here, but Excel is not able to compute any t-statistic, any standard error, any p-value. So we're not able to evaluate whether these effects are significant enough or not, whether they're just results of random variation. So what we're going to do now is that we're going to make a normal plot of these effects. So I'm going to take a copy of the effects here and the labels, put it over here. Right. And then I'm going to make a normal plot. And I made another video about normal plots. So if you don't know what that is, you can check out that video. So I'm going to sort these effects. So I choose sort and I choose customized definition here. Oh, let's try again. In fact, I'll select all of these, choose sort and user defined or customized sort, and I'll like to sort my elements using column M because that contains the actual numbers here. And I'd like to go from least to largest here. That's what it says in Danish. I'll just click OK. So now I have sorted them starting with the smallest effect, ending with the largest. And I'll just give them a number. So this is the effect, or a value rather, and this is the effect. And then we have an order, which is just its number in the ordered list here, like that, like that. Whoop, 16, like that. And then I'm going to compute what we call a rank or ranked, and that's just equal to the order minus 1/2 divided by the total number of elements in this list, which is 16. And I'll make a copy of that all the way down here, like that. And what I'm going to do now is to find the quantile of this rank here in a standard normal distribution. So I'll write norm.inverse, and I'll input the rank, and then 0 for the mean, 1 for the standard deviation, so that I get a standard normal distribution. So that's my quantile. I'll copy that all the way down here, like that. So what I have now is a list of effects ordered from least to largest, and then the corresponding quantiles for a sample of 16 observations. The corresponding quantiles from a standard normal distribution, that is. I'm going to plot that. So I'm going to insert a plot, which I already did, and then I'm going to select data. And I'll just remove this series, add a new series. The X values are going to be my quantile, my standard normal quantiles. And the Y values are going to be my effects here, like that. So I don't care about title or anything. Let's just look at the plot. And what you see here is that some of these effects are lined up here, and that is the signature of the standard normal distribution. That means that these effects here have somewhat a standard normal distribution, more or less. However, you can see that some of these points deviate from this line. For example, this one, that's clearly a deviation. This point is the largest one, it's 35, so it corresponds to the intercept. So what we can say is the intercept is definitely significantly different from 0. The same thing goes for this point here, which is the second largest one, that's the enzyme concentration. So the enzyme concentration has an effect which is significantly different from 0. And I would also say that this one, so that's the temperature, is deviating from the line, and this one and this one. So that's the stirring. So I would say that these effects definitely are significant. Let's just give them a yellow color here. But if you go to the small effect, the negative effects here, at least 3 of them I would say deviate from the line here. So the 3 smallest effect here, the pH, the interaction between A and C, so that's the enzyme concentration and the pH, and the interaction between, that must be the pH, and the stirring, they are significant as well. So just by looking at this plot, we can determine what effects seem to be significant and which seem not to be. These effects, and notice that all of the 3rd order interactions are among these in the 4th order as well. Typically, they would be non-significant. The reason, so what we're saying is that they're really, the true average value of these effects is 0. The reason they're not exactly 0 is because of random variation. So they distribute themselves normally around 0,